Looking at this first example, we're given concentric circles. Concentric circles have the same center but different radii. And so we are given 15 for PB and 17 for PA. If the radius is drawn to this point of tangency, which we need to assume, at point B, then it forms a right angle. Not only that, but it bisects the chord that it forms the right angle with. And so this is an 8, 15, 17. That means that BC is also going to be 8. And if we're looking for AC, that's the two parts combined, which would be 16 units. Here are two common tangent problems. In this first problem, I've already marked that the radii are 3 and 4. We want to figure out the common internal tangent given PQ is 25. And so if you remember the common tangent procedure, we connect the line of centers. The radii are already drawn into the points of tangency. And then the last piece is to draw a segment parallel to the tangent from the smaller circle center. And then I'm going to draw in this auxiliary segment. And from here, I'm going to carry over the radius of P to this side of the big right triangle, which is 7. And I was given the line of centers is 25. And so if we could get this part of the big right triangle, then that would translate to the opposite side of the rectangle, which is our common internal tangent. So if you remember, 25 and 7 paired with 24 make up the Pythagorean triple, which then would translate to the side of the rectangle, making our official answer 24 units. In this next problem, we're given a common external tangent. We are given the radii are 2 and 7 units, and the distance between the two circles along the line of centers is 4. And so the line of centers is already drawn for us. The radii are also drawn for us. We form right angles when we draw the radii to the points of tangency. The last piece, from the smaller circle center, draw a line parallel to the common tangent, forming the right triangle. And so here we want to figure out what's the missing part of this right triangle, so that we can figure out then the missing part of the rectangle, which is our common tangent. And so from here, I'm going to take the 2 and circle O and translate it across. Not drawn to scale, that means that this part of the right triangle is 5. If I carry over my radii, the radius of circle P is 7. The radius of circle O is 2, which makes the hypotenuse on this triangle 13. And then if you recognize, we have a 5, 13, that's 12. And so the common tangent winds up being 12 units. These last two examples are walk-around problems. And so in this first one, we have 3 circles externally tangent, and we are given the segments that connect the centers of the circles, and we'd like to figure out the radius of each circle. So pick any circle to start with. I'm going to go ahead and pick circle B and assign the radii to be x. And I'm going to walk around clockwise. You could walk around counterclockwise. You could also walk around from both directions in this example. Here, I'd get that if BC is 19, then radius of C, circle C, is going to be 19 minus x. That's going to be the radius here then, since radii in a circle are congruent. And then that makes radius of A, well, if AC is 16, then 16 minus whatever 19 minus x is going to get us the radius of A. And so that will wind up being negative 3 plus x. And if you look at where we ended, we have 2 different values that we can add together, x and negative 3 plus x, to get the segment length AB, which is 11. Combining like terms and solving our 2-step, we get that the radius of circle A is 7. So radius of circle A is 7. Had I taken a minute to actually read the problem and see that we wanted the radius of circle C, I would have let the radius of circle C be x, so that when I solved for x, I had my answer. That being said, I can go ahead and take 19 minus 7 and get 12 units for the radius of circle C. And then if you look at the last one here, we want to start, let's actually look at it. We have a circumscribed quadrilateral, so a circle that touches each point externally in the quadrilateral, and we would like to figure out the measure of AD. So since I don't know any part of AD, I'm going to go ahead and assign part of it to be x, and then we're going to walk around. So I'm going to go clockwise again. The key here being that if 2 tangents extend from the same point, then they are congruent. Tangents to a circle, I should say. And so walking around, if I had that the part coming off from A is x, then that will extend on the side that has 10, which means that the part that has 2 tick marks is going to be 10 minus x. And then this part of the circle from C, the tangent from C, is going to be 7 minus whatever 10 minus x is. So that's going to be negative 3 plus x. And If this whole segment is 14, then 14 minus the negative 3 plus x is going to be the last part here, which would be 17 minus x. And now I have two expressions that make up my missing side. X plus 17 minus x is going to be the measure of AD, and the x's canceled, leaving me with 17 units for AD.